Good morning, good afternoon, or good night. Depends from where you are listening to me. Before starting my talk, I would like to mention some knowledge you should have to follow my presentation. And that will be a basic course on physical chemistry, a basic course in quantum chemistry, and a basic course on statistical thermodynamics. Thank you. I'm going to talk today about the Ornstein-Zernike equation. The Ornstein-Zernike equation is an integral equation that relates two correlation functions. One of these correlation functions we have seen before, and that is the radial distribution function, but in the context of the Ornstein-Zernike equation, it has the name of indirect correlation function or the total correlation function, and it is a consequence of what we have seen before, the radial distribution function. The total correlation function is just the pair distribution function minus 1. Pair in the context here that you are treating central field potential. This integral equation, the solution of this integral equation is going to be discussed. Not the numerical solution, but the general aspect of these functions. But first, in this chapter, we are going to prove correlation function. We are going to prove the Ornstein-Zernike. We are going to discuss this integral equation and its limitations. Consider now three particles in this sequence 1, 3, and 2. There will be a direct interaction between 1 and 3, and also a direct interaction between 3 and 2. And consequently, there will be an indirect interaction between 1 and 2. This sequence of interaction I'm going to represent by that. The underline here is to say it's meant to be that the three particle, it's meant to be that particle 3 is between 1 and 2. And if you add all the contributions from the particle 3, I'm integrating over the volume of the particle 3. That's the notation I'm going to use. I'm adding all the direct interaction 1 and 3 and 3 and 2, and there is an n here to take in account all these particles, and the volume is in the denominator, just to make this integral with no dimension, since the correlation function has no dimension. I have add all the contribution and transform it to the integral. There is another, the proof I'm going to give here is a very simple one, a didactical one, but it is not the way it was proved originally by Ornstein-Zernike. Ornstein-Zernike did it in a statistical way, in fluctuations, considering fluctuations. And there is several other ways to prove Ornstein-Zernike, such as using graph theory or using functional density. But that's the simplest one, and you arrive in the Ornstein-Zernike in a didactical way. Let's continue the interaction. Let's put the particle 4 in between 1 and 2 and after 3. That will be the contribution of 3. That will be the contribution of 4. And then I integrate again, rearrange, use this again. And when I use this for particle 1 and 2, particle 3 and 2, I will end up with that. The process, you see here on the second interaction, the total correlation function has appeared under the integral symbol. So the h function appear outside and inside. And if you continue the process again, and use this expression recursively, this one and this one, just substitute, I'm going to arrive at the Ornstein-Zernike equation, which I will put it in this form. The indirect correlation function is equal to the direct correlation function plus the density, an integral over h and c. And you see that this is not a self-contained integral, because h is inside and outside. Let's say it's one equation with two unknowns. How to solve that? It's going to be the next discussion. To solve the Ornstein-Zernike equation, you need an extra information. You need something that will connect C and H. You need something that relates the indirect correlation function to the direct correlation function. And this is called a closure relation. The most used closure relation, there is several, but the one we are going to use here is the Perkus-Iavik closure relation, which is given by that. You see, there is a relation between C and H that you have to substitute back on the Ornstein-Zernike equation, modify the equation, and solve the integral equation. But you see there is a plus exponential of the potential here, and for computational purpose that's not very good, that's not very nice, because it can give overflow on the computer. Therefore we define a new quantity, which is the difference between H and C, which is actually the not by gamma, which is actually the integral part of the Ornstein-Zernike. You can see it here, it's in the integral here. But if you manipulate this expression as done here, you arrive at that. And you modify the plus exponential to the minus exponential. That's much better to handle computationally. So equation 7 is used in computational codes because of gamma is more appropriate to handle. But what I want to emphasize here, that you need some extra information to solve the Ornstein-Zernike equation. There is several closure relations, and this is the extra information, is called closure relation, and there is several closure relation. In one of those, the one that we are going to use here is the Perkus-Iavik closure relation. It's necessary, it's convenient to define two another functions in liquid theory. One of these is the cavity function, which is defined by that. That's y, this is the cavity function, or that, which has a interesting interpretation. The cavity function is a correction to the Boltzmann factor. If you have a potential, you have the Boltzmann factor. If you want to get the radial distribution function, you multiply it by y. For gases, the y is going to be 1, and there is a y you can expand it also in densities, like 1 plus coefficient 1 times density, and so on. So they can be very useful. And for hard sphere, it's a continuous function, as you are going to see. Another important function is the bridge function. The Perks-Iavik closure relation is just a special case of this expression. Actually, all the closure relation they can be put in this form. You have just to choose the convenient B to make a closure relation. For example, if B equals 0, you get this closure relation, which is called a hypernet chain closure relation. If you put that, is the mean spherical approximation, and you get this relation, actually this relation. So you have another kind of relation between C and gamma, or C and the potential energy, and if you put B of R equals that, which I leave for the problem 2 in this chapter, you obtain again the Perks-Iavik closure relation. Let's go to problem 2. That is the problem 2, and I ask you to substitute that in the general relation I gave before to obtain the Perks-Iavik closure relation. So it's very simple, just develop this algebra here. I'd like to talk now about the thermodynamic consistency, which can be obtained if you integrate the Ornstein-Zernike using bipolar coordinates. Any book of mathematical physics you find it. So you transform it to this expression, define these variables, and make the integration. Again, the algebra is very simple, and you arrive at the equation 18, which is very important. H and C have to satisfy that, and usually they don't, because of the closure relation. Closure relation is an approximation to solve Ornstein-Zernike equation, and at the end you cannot always satisfy with some precision the thermodynamic consistency. As an application of this equation 18, consider that you have this expression. For example, you can prove it in a simple way again for the gas phase. It's using the real expansion, and then you generalize. But the point here is if you have this, you can invert to obtain that by using this expression. Because if you multiply one by the other, it's going to have to be 1, and if you multiply this one by this one, you're going to have 1 as well. So just a way, a simple example how to use the consistency equation. All the models, they have to satisfy equation 18, which I did here for one dimension. For the problems, I have only 2 problems. The second one we have already discussed. That is to given this bridge function to prove that the Perks-Iavik closure relation is given by that. It just follow the algebra. And the first one is to make a connection between cavity function and the bridge function. To prove that is given by that, you just have to use this expression for g of r and substitute it on equation 57.9. That is the general relation between the correlation function and the bridge function. Use that in this general expression, you got the desired result. Thank you very much.